let's get started with lecture 13. So today I want to wrap up the discussion of oscillations. So there are a couple of minor points, short topics that we will discuss regarding damped and driven oscillations. And then my plan is to start on traveling waves. So that's chapter 16 of the textbook. So last time we mainly talked about the pendulum. And we discussed an ideal pendulum where it's just a mass hanging from a massless string of length L. We also talked about the more physical pendulum, which is some rigid object with an axis going through it. So let's say that's the pivot point here, and there's a center of it has a center of mass distance L away from the pivot point, and then the total mass is m. So we derived a couple of formulas for the period of these two, and we had a little bit of practice solving problems involving pendulum. So the general formula we derived here for the physical pendulum was using tau equal I alpha, and we said, well, tau is going to be counterclockwise, and it's going to be, if this angle is theta from the vertical direction, it's going to be minus mg the force times L sine theta, which we can approximate by minus mg L theta for small angles, and that's I, the moment of inertia around the pivot point, times alpha, which is the second derivative of theta with respect to time. So from this, we found that the second derivative of theta with respect to time is minus mgl over I times theta in the limit of small oscillations, and then this is the number we identify with omega squared, so we found that omega is the square root of that coefficient there. The simple pendulum is just a special case of that, right? The moment of inertia around this point, it's rotating around that point, the point where the string is connected to the ceiling, is just m times L squared, and then we get omega is equal to G over L, right? So the m's cancel out. One of the L's in L squared cancels out with the L in the numerator. All right, so the next topic I want to start today is something known as damped oscillations. So basically, so far, we focused on cases where there was no friction, right? Energy is conserved, you just keep going back and forth. There's no loss of energy to heat, and everything is perfect. And that's not realistic, right? In most realistic systems, there's some type of friction or drag force which takes away energy from the system. The system heats up as it moves, and it's going to lose its energy and eventually stop moving. So a very simple and widely used model is where you have a drag force. So we have, let's say, F drag is minus the velocity times some number, some coefficient. So let's call that B. So first, it's a type of force that's opposing the motion, right? The direction is always opposite to the direction of the velocity, right? A constant friction has the same property. That's why it's not a conserved force. It's a constant force, but it depends on the direction of motion. If you're moving to the right, it's minus F, and if you're moving to the left, it's plus F. It's always in the opposite direction. So here, a drag force, which you would get, for example, from air resistance, as opposed to rubbing against the surface, it also depends on the speed of your motion. So the slower you move, there's less resistance to your motion. So this is just a particular model. You may remember other types of drag forces that are proportional to velocity squared, right? That's what you would get for a gas that's kind of being driven away in a turbulent way as you move into it. So there are various models. I think the linear drag that we're focusing on here is known as the laminar drag. So it's like the fluid you're moving into kind of moves in smooth layers, and that gives rise to the linear behavior. You may have quadratic behavior, kind of the turbulent type of motion that you really mess up the liquid or gas around you as you move, and then your dependence on speed is even stronger. It goes as velocity squared. But so we're going to focus on this particular model of a resistance force to motion that's linear with the speed. All right, so what happens if I again write my equation? So suppose again I focus on, let's say, a mass on a spring, an idealized model. However, I also have this drag force. Well, again, F is equal to ma, but now F is minus kx minus bv, and that's equal to ma. So in terms of, if I express both velocity and acceleration as derivatives of position, I have minus kx minus b dx dt. The first derivative with respect to time is equal to mass times the second derivative with respect to time of the displacement from the equilibrium position. So that's the equation that governs the dynamics of the system. And so a type of equation like this is known as a differential equation. Many of you have not taken a course on differential equations, so it's generally not easy to give an equation and then find the functional form of position as a function of time, sort of what we've been doing even for the simple harmonic oscillator where b is 0, right? We don't have that drag term. We say, well, that's the equation, and then we somehow have the solution and we just verify that it works. So that's our strategy here. So I'm just going to write down the general solution to this equation, and then we plug it in and verify that it satisfies that equation. So then it implies that a system governed by these forces, so spring force, a kind of restoring force proportional to displacement, and a drag force proportional to the velocity, will behave like that. So here's our solution. X of t is a e to the minus b over 2m times t cosine omega t plus phi naught. And then we're going to find omega. So it turns out that the frequency changes when b is non-zero, from the case where b is 0. All right, so first let's get some intuition about this. It makes a lot of sense, right? So for b equals 0, you will have oscillations whose amplitude kind of remain constant because there's no energy loss in our system. And then for b not 0, see, it's like the same thing, except omega is a different frequency, but but it's multiplied by a term, e to the minus something times t. So what does e to the minus something times t look like? So let's say this is t, this is e to the minus whatever, some number, which in this case is b over 2m times t. Well, at t equal 0, it's 1. And you see when you make t large, it's going to come down quite rapidly, right? It's exponentially decaying. So every time you kind of add a time 1 over alpha, let's say, it's like you divide your value by e, which is a number larger than 1. So it's really killing off that curve quickly. And then once you multiply something like this by something like that, well, you're going to get an envelope from the exponential decay. So that's not our curve, it's just an envelope. And then the cosine term will somehow go between these, right? That's the result of the multiplication. So this is our real time dependence. It makes a lot of sense. It has oscillations with some frequency, and then the amplitude itself goes down as time goes on, and the system is losing energy. Let me correct my drawing a little bit here. See, at the envelope, right, is equal to 1 at t equal t equals 0. So at t equals 0, the envelope should touch our curve. So let's say, yeah, a little bit like that. Yeah. So that's better. So this is x of t here, and this is t. Another thing to notice is that, yeah, it's decaying very fast, right? It's going down. But every fixed time, let's say 1 over whatever is multiplying time, which is here like 2m over b. 2m over b must have dimensions of time, so the exponent is dimensionless. So every time you add 2m over b to your total time, you divide the amplitude by a factor of e. So it's going down very fast, but it's not going to be 0 all the way up to t equal infinity, right? Suppose you keep dividing by 2, right? It becomes very, very small. So after one of these intervals is half, after 2 is a quarter, after that it's 1 over 8, 1 over 16, and suddenly, you know, once you reach, I don't know, 2 to the 1,000, that's I don't know, it's a really large number. It's 10 to the so I think 2 to the 10 is, I think, around 1,000, so that's probably 10 to 100 or something like that. And E is around 2.7, so it's even a faster decay than that. All right, so the strategy to see that it works, I don't want to go through the entire calculation, is but let's just give you an overview of what the strategy is. Well, so I have this functional form. I can take its derivative with respect to time, right? So the first derivative, for example, gives me one term where I take the derivative of the exponential. It just gives me a factor of minus b over 2m. Then I have another term where I take the derivative of the cosine, which gives me a factor of omega for the argument of the cosine, and then turns the cosine into sine. And then once you take the second derivative, you get 4 terms, right? So each of those 2 terms, again, is a product of an exponential times a sine or a cosine. So each of them, using the derivative rule for products, you know, gives 2 terms. So I'm going to get 4 terms for the second derivative. And these 4 terms, you know, have some coefficients, and each of them is that exponential times a sine or a cosine, the first derivative term similarly has the exponential times a sine and a cosine, x has the exponential just times a cosine, and then we need to have this equation satisfied at all times. Omega squared is k over m minus b squared over 2m squared. So notice that when b is 0, this has to be the same as a simple harmonic oscillator we studied before, which had omega squared equal k over m. So omega gets smaller in the presence of damping, which means the period gets larger. So somehow these oscillations take longer time for each cycle. So omega becomes square root of k over m minus b squared over 2m squared. All right. Notice that the dimensions work, right? So b over m, again, we're saying the argument of the exponential must be dimensionless. So b over m has dimension 1 over time, and omega has the same dimension as b over m, and that's fine. Omega is just 2 pi over a period. The period has dimensions of time. Okay, so that's that's a summary of our understanding of damped oscillations in the presence of a linear drag force that's relevant to laminar flow. So we get an envelope with exponential decay for the amplitude, and then the frequency or the angular frequency gets reduced by a certain amount that depends on the coefficient b. Again, as a reminder, the drag force was minus b times the velocity. So remember, in a simple harmonic motion, the energy had to do with amplitude squared, right? If you think about the potential energy, for example, it's 1/2 k x squared. So if the amplitude gets killed off by this exponential factor e to the minus b over 2n, the way the energy is being taken out of the system, the way the total energy in the system will decay, will be that factor squared. So we find this important relationship for energy decay, which is E of t, say total energy, total mechanical energy. Of course, total energy of the universe is conserved, right? This energy is converted to heat in the fluid that's causing the drag force. But the mechanical energy of this mass that's oscillating is going to go as like E of 0, the initial energy, times e to the minus b over m times time, right? So m over b sets a characteristic time scale. So let's call m over b to be tau. Then E goes as the initial energy times e to the minus t over tau, right? So if you think of the total energy, every time a time tau passes, you divide your total energy by a factor of E, 2.7 something. All right, so let's take a look at a couple of slides basically summarizing what we were talking about. So if you have this drag force, that's the solution. Omega goes down. This omega naught squared k over m is just the angular frequency in the absence of damping. And that's the overall shape. There's an envelope for the amplitude, so the amplitude goes down as time goes on. And And this is the exponential decay of the energy, which we talked about, right? So, for example, after a time t, your energy gets divided by E, so it becomes 37%. Then again, if you divide it by E, it becomes 13%, and it gets killed off relatively quickly. If tau is a reasonably small number. Of course, if tau goes to infinity, it doesn't get killed off, which is the case where b is equal to 0, right? Tau is inversely proportional to this drag or damping coefficient. All right. So that's all I wanted to say about damped oscillations. There's another topic, we don't do anything quantitative about it. It's called resonance or driven oscillation. So in the same way that you can have friction slowing down your oscillations and taking away energy from it, you can imagine like putting in energy into your system, right? Imagine like a kid on a swing in a playground, right? And she's swinging back and forth, and every time, like, it's basically like a pendulum, but every time she reaches all the way back and is going to turn around and move forward, you give her a small push, right? So you keep like giving pushes at the right time, right? And it's putting some energy into the system. So it's kind of, you can already from this example build some intuition about how you can be more effective in driving an oscillatory system, right? So a pendulum has a natural frequency for oscillations, right? So every time it comes all the way back, it's like one period has passed. So if you time your pushes accurately to coincide with the period, which means your force, the force you use to drive the system, has the same frequency as the natural oscillation of the system, you're going to be very effective. You're going to put a lot of energy into the system. On the other hand, if you're just randomly, like, imagine this kid is swinging and you randomly at sometimes push this way, sometimes push that way, you don't care where it is or what's the direction of the velocity, well, sometimes you speed up, sometimes you slow down, right? So that's not going to be very helpful in driving the system. An example is you've probably seen these examples of like a sound shattering a glass, right? So sound, has some pressure waves in the air. So locally, if you look at one position on the glass, basically the air molecules are oscillating. So the pressure of air is oscillating in some way. And then if it turns out that the frequency of those oscillations coincide with the natural frequency of oscillations of the glass, you can put a lot of energy and destroy it. So that's kind of a general idea about how the amplitude of a driven oscillation depends on the frequency of the drive, right? So suppose the force you're applying to the system also has a sinusoidal dependence on time with some frequency, let's say f external here, right? That's the frequency of the force that's driving the system. And the system has some natural frequency for oscillations. So when these two coincide, so when f external is the same as the natural frequency of oscillations, you're going to get a peak in amplitude. It means your driving is effective in increasing the amplitude of oscillations, in putting energy into the system. Okay. So let's take a look at the summary of what we did in chapter 15. So we talked about a horizontal spring, a vertical spring, a simple pendulum, a physical pendulum. In all cases, right, there was a restoring force that was proportional to the displacement, right? We had the second derivative of some quantity, either an angle or a distance or something like that, being equal to a negative number times the quantity itself. And these systems give rise to sinusoidal oscillatory dynamics. The energy is conserved. We have kinetic plus potential energy in these systems. We talked a little bit about damped oscillations. So if there's damping energy that is not conserved, there's a time constant for the decay of the total energy. This was the general form of the displacement, right? We had the amplitude, we had the angular frequency, or the period. These were three related numbers that describe, how stretched out our curve is in this direction. The amplitude says like how large the oscillations get in this direction. We had this very useful mapping between circular motion and oscillatory motion. So that was very helpful in problem solving, in finding, for example, the initial condition or the phase constant. And we briefly mentioned resonance and damping. So when you have damping characterized by a linear drag force, basically what it does, it multiplies your solution by an exponential decaying factor, and it also reduces omega in a particular way. Okay, yeah, that's the end of chapter 15. So next topic, we're going to get started on waves, on traveling waves. So when we were talking about oscillations, mostly we were thinking about something that's local in space, right? It's somewhere. And just as a function of time, it performs this repetitive back and forth motion. Waves are a bit different, right? They're extended in space. So from experience, you may be familiar with maybe dropping some water droplets into a body of water, right? So every time you drop something into the water, you generate a circular wavefront that moves away from it. So let's just start with an overview of the content of chapter 16 on traveling waves. So yeah, so first we're going to start by just gaining some intuition about what waves are. So the idea is that you kind of disturb a medium, you kick a system at some point, kind of a connected, extended system at one point, like dropping something into a body of water, or having a stretched string, a rope, and you kind of give a kick to one end of it. You move it up and down quickly and generate a pulse. Or you have some springs attached together, and again you push and pull quickly one end of it. Or we speak and maybe you hit a drum, and then you kind of disturb the air molecules somewhere, and again this disturbance kind of propagates in that medium. So that's a general idea of a wave, and waves in general come in two categories, let's say. So there are longitudinal waves where this displacement is parallel to the direction of travel. So that's kind of, you have these springs connected to one another, and then maybe you take one end and push it and pull it back, right? And then there is this area of compression that travels along the system of springs, or maybe the displacement is perpendicular. So if you have a stretched rope and you pull one end of it up and bring it down, you generate a pulse that moves away from the source of this disturbance. So that's known as a transverse wave, where the actual displacements from the equilibrium position displacements are perpendicular to the direction that they propagate. So we'll get some practice with these concepts. Somehow for oscillators, we just needed to talk about frequency and amplitude. Now, for waves, like especially sinusoidal waves, so where this disturbance has sinusoidal dependence on time, so it's not just one pulse that you generate. So at the source you keep generating sinusoidal oscillations, and then they keep kind of propagating away from the source. So in addition to frequency and amplitude, which we talked about for oscillators, we have to talk about wavelength and wave speed. So wave speed is kind of clear. It's how fast these disturbances propagate away from the source, or propagate in the medium in general. And then we talk about wavelength. So it's the distance between, for example, peaks, but not in time as a function of position. So we'll talk about these things, and there are, of course, some relationships between them that we discuss. So that's kind of a general kinematic description of wave phenomena. So two examples, prominent examples of waves are, of course, sound waves and light waves. Sound waves are longitudinal waves in the pressure, for example, of the air. Light waves can be viewed as transverse waves in the electric and magnetic fields that are perpendicular to the direction of propagation. We gain some intuition about the color of light, how it corresponds to different wavelengths or frequencies, and the pitch of sound again depends on frequency. We talk about energy transfer by waves, how they carry energy, and we talk about the Doppler effect. It's an important phenomenon where the source itself is moving. So typical example would be I don't know, a police car with a siren, right, that's driving past you. It's generating loud sound waves that you can hear, but then it's moving relative to you who are hearing those sounds. Or again, the light from moving stars, for example, or moving planets. Again, there are consequences for the wavelength that we observe when the source itself is moving relative to the observer. So we discuss the Doppler effect, and that's roughly an overview or a preview of what we'll be talking about in this chapter. So so let's get started. Again, you've all seen this is a very nice picture of probably something dropped into this water and it generated these wavefronts that are moving away. They're traveling away from the source of the disturbance. Talk about a medium. So that's really for a mechanical wave at least, it's a substance which carries the disturbance, right? So we talk about some displacement, and these displacements are in something. So here, for example, it's in the surface height of this body of water, for example. The water is the medium that carries the wave. All right, so we're going to spend a lot of time talking about the transverse wave in a rope or a string. So again, these are quite common in musical instruments, right? A guitar string or a piano string can support waves along it. And the simplest example is you have a stretched rope and you take one end of it and you quickly move it up and down. So you generate this pulse and then it travels along. So let's first try to think a little bit about why it should be moving away or traveling. So let's say traveling waves. So consider a rope, right? So you fix one end of it and it's under tension, and then you take this point, move it up, and then move it down. Right? You grab one end of this rope that's under tension, that's stretched out, you move it up and down. Okay, so looking closely, you can already see what's happening. So assume, the rope is here. This end you've pulled up slightly. So as you pull up, if you look at this tiny piece over here, or this tiny piece over here, right? Let's look at this tiny piece over here. So roughly speaking, if you've pulled up this end, if you think about the tension on it, on this little piece, because you've pulled this up, you've caused this angle in your rope, so the tension to the right should be, so let's say that's our piece of rope. And then this is the rest of the rope. So you see the tension to the right, to where you've pulled the rope up, has more of an upward component, right? If you think about these forces in the vertical direction, as you pull this up, you pull up, the pieces that are next, that are coming after, right? Not just at that point, but you change the direction of the tension a little bit as you move a tiny piece up, and that pulls along like the rest of the rope, at least the nearby pieces with it, right? So kind of this motion that you created at one end in some way will be injected into the medium, right? And then, once this piece moves up, it pulls up the piece next to it. So this upward displacement from the horizontal flat equilibrium position keeps shifting to the right, away from the source, away from the point where you created this disturbance. And then if you go up a little bit and then you bring it down. Again now, suppose you bring it down a little bit now. So you create maybe a kink, so something like this. And thinking about this piece over here, it's going to be some tension this way and some tension that way. So now as you pull the rope down, you bring down pieces that are next to it, and each piece that comes down will pull down a neighboring piece. So the net effect of this is that your disturbance travels away from the source. And it turns out, although we don't really prove it, that this propagation occurs at constant speed that only depends on the properties of the medium. So in this case, it depends on its tension, for the case of a string, and its linear mass density, how much mass there is per unit length of your rope. So there's going to be a constant speed for the disturbance to move away from the source, or move or travel through this medium. All right, so then what should happen? I think it's helpful to look at a simulation of this to see what's going on. Okay, so I'm going to generate a pulse. So this is basically string modeled by a bunch of beads that are connected together, let's say. So this green bead here is attached to that rod that I just moved up and down. And it's going to generate a pulse. So we imagine that somewhere in the far distance this string is attached to something. So it's kind of like this, but really far away. Because here, it's going to get reflected, and right now we don't want to think about the reflection from here. So let's say there's no end, it keeps going, right? Okay, so let me just generate the pulse here. See, I move it up and down, right? And now at this instance right here, this green one exerts an upward force on this red one, and the red one is exerting a horizontal force on it. So this red one will be pulled up. Yeah, so let's do this again and pause it here. Okay, so see, a little bit later, this one gets pulled up, right? Now you can imagine at the top what happens once you kind of get past the peak, right? This green one here experiences a horizontal force from the beat afterwards, but a downward force, right? Because there's tension in the string from the beat before it. So the ones that were previously up now begin to come down, and you just get this pulse with the kind of the same shape, just traveling through your medium. So keep your eye on the green one. Let me run it again. Keep your eye on maybe this one, on the green ones, right? So we pull this up, we push this down, so here this gets pulled up and then gets pulled down. Gets pulled up here by the ones before and then gets pulled down by the ones before. So, and there's nothing special about the green, it's just the guide to think about it. So it happens to every bead, or every piece of the rope if we're thinking about a physical rope. So we get this pulse shape that just travels at some constant speed along the string. Now, as I mentioned before, the speed depends only on the tension and the linear density, how much mass your rope has per unit length. This is a picture of an actual experiment. So this is a real pulse, and you see it just keeps moving to the right. And the speed is, well, square root of t, the tension, divided by mu, where mu is the linear mass density. We're not proving this here. There's an advanced topic chapter or section rather, in the book that talks about the wave equation and its solution. So it uses kind of partial differential equations, and I think it's a little bit above the level of this class to try and derive this. But I encourage you to read up if you're interested. So let's take this formula, right? So there is a formula that can be derived for the speed of the propagation of a disturbance. And as you see, the higher the tension, it makes sense. The forces are larger somehow. You expect the pulse to travel faster. And the higher the amount of mass per unit length, the linear mass density, you have more inertia, so you expect that to slow things down. All right. So let's write this equation in the notes here. It's an important equation. So speed of propagation for transverse wave on string. So tension T, mu is mass divided by length, right? We think of our rope or string as a one-dimensional thing, so how much mass there is per unit length. And we're saying V is the square root of tension over n. So what does it mean? Well, basically, if the pulse has a shape, right? If you think about a snapshot graph, so at some instance in time you take a picture of your rope and it looks like that. There's some pulse. So I don't know, let's make it a little bit asymmetric so it maybe looks like this, right? There's some pulse, so some pieces of the rope are are away from their equilibrium position, and that's in the transverse direction, perpendicular to the direction of propagation. So when we say the wave or the pulse has a certain speed, it means, well, a little bit later, so let's say this is at t equals 0, I just take a picture, start my timer, and then that's the initial time, and a little bit later, let's say at t, I don't know, equal to whatever, later, larger than 0. So I look at it. So if every disturbance, which means every height, is moved at constant speed, so this point that's a certain height above, and this point at a different height above, they both move like by the same distance, right? So this is going to be here. The distance between them will be the same. So it's like you have the same shape, just transferred a little bit away. So if I go here, my pulse shape would look something like this a little bit later. So it means if you take another snapshot, if you take another picture of this entire rope, a little bit later, these are at the same height here, you just see this pulse which has moved some distance to the left, the entire thing, and let's say that distance we call, so let's say from here to here, this is the beginning of the pulse. Let's call this L. Right? So L must be equal to velocity of propagation times time. Okay? So that's one way of thinking about wave propagation in terms of these snapshot pictures. Okay, let's do a quick check question. So pause the video and try to figure out the correct answer. All right, so two wave pulses travel along the same stretched string, one after the other, and which is true. So what can we say here? Well, so what's the difference between these two? It's the shape of the pulse, right? Which is basically like at the source, how much we pulled it up and then brought it down, right? How we generated the pulse shape at the source, how fast and by how much you move one end, let's say at the source where you generate the disturbance. But we know that the speed of propagation doesn't really depend on that. It only depends on two things, on the tension in the string and on its mass per unit length, on its linear mass density. So if it's the same rope, those two things are the same, and the answer should be C, right? It shouldn't depend on the pulse shape or how it was generated. All right, here's another one. Again, pause the video and try to find the correct answer. Okay, so what does it say? So we have this wave on a string that travels twice as fast. Okay, so in order to make a wave on a string travel twice as fast, what should we do to the string tension? So the assumption is that it's the same string, it has the same linear mass density. And we know that the speed is proportional to the square root of t. It's the square root of tension divided by linear mass density. So we have to increase it by a factor of 4. So the square root of 4 is 2, and we get a factor of 2 in our speed. All right, this is a picture of what we discussed on the notes a little bit before, thinking about the snapshot of a pulse. So it's traveling at some speed. It has a leading edge, it has a trailing edge, And then basically you just shift this entire disturbance by some distance L that's equal to the speed times time a little bit later, and that's what you see if you take a picture of this entire system a little bit later. All right, I think that's a good place, that's a good place to stop. So we'll continue the discussion of traveling waves in the next lecture.